There you go.
Yeah. Make sure I don't write outside the. You can let me know if I do that.
All right.
Hey guys. This is probably the most important lecture of the whole year. So pay extra close attention and interact, as much as you can. If you don't understand something, ask questions. And the reason is because I'm introducing a wonderfully simple concept, but there's a lot of sneaky, subtle things in it, and that's Newton's laws of motion. So we're going to talk about Newton's laws of motion. So is this still in the frame, bud?
Sort of. Well, half. You gotta go this then.
Well, then let's zoom out just a tad.
Yeah, see? Right. Zoom out.
Okay. Newton's. So I've decided to do this just totally kind of free-handedly, freestyle, no notes, just all from my noodle here. Newton's laws of motion. And I've been, because this is what I'm actually, one of the classes I'm taking to grad school is actually mechanics. The professor is very good at pointing out some really subtle things. We're not using Newton's laws right now. We're using another formulation called Lagrangian mechanics, which we're not going to get to at all. But he's going through and kind of having us rethink about some of these mechanics ideas very carefully. So Newton's law of motion. And these ideas are about 350 years old. Newton was probably the most important moment in the history of science was the publication of the Principia Mathematica. That's the basis of calculus, the basis of modern mechanics. Everything that is not modern physics being quantum mechanics, and some would classify the stuff that Einstein did as modern physics, but I'd say in some way it's still related to this. So I want to make some assumptions that are different than, like, I remember we started the class, we kind of, just for fun, we started out talking about relativity and how simultaneity is something that's relative to an observer. I'm going to say that doesn't apply here. We're going to assume that there's a universal frame of reference. According to Newton, 350 years ago, this would be kind of God's frame of reference, or the frame of reference of the stars, as they don't seem to them, they didn't really appear to move at that time. So that would be our frame of reference. And also time is invariant. No matter where you go, time is always the same. It's God's watch. It's not relativistic. So we'll make those assumptions. We'll start out with a very kind of archaic view of the universe, and just hold to those assumptions.
That's pretty long.
But now, in modern physicists, we have some exception to those rules. But for the most part, they actually work pretty good. So Newton's first law. Objects in motion Yeah, I'm a terrible speller. Object. Yeah, that better?
Yeah.
Objects in motion tend to stay. Some of you guys have probably heard this before. Stay in motion. Some people don't like my eyes. They say they look like hyphens or upside down exclamation marks. Objects in motion tend to stay in motion. Objects at rest. Tend stay at rest. Now these two statements are the converse of each other. It's basically the same statement, just kind of reworded. Now, this also has to do with like objects going in a straight line. Because remember, motion is relative. So we can, obviously, you know, in the world frame or God's frame or whatever, every object has some kind of velocity. But if I'm going in a straight line, I'm going to continue going in a straight line unless something pushes on me and causes me to kind of get deflected. So if you have an object in space, you throw it out there, as long as you're deep enough in space away from like the gravitational effect of stars or other planets or other massive objects in the universe, you're going to continue going on a straight line forever. It would never slow down. It'll just keep going and keep going and keep going. And in order to, if I had an object and I just set it there, again, we're talking about kind of this God frame where we have this absolute frame of rest. We could just set something there at rest. Is it going to move? No, it'll stay there eternally. Does not move. Okay. Now Newton's second law. Now I want to give you, and I'm in a little bit dangerous waters here, pedagogically speaking. I'm going to give you the most general form of Newton's law. And that, hopefully that doesn't confuse you, but please stop me if you get confused. But the wonderful thing about this is it's so incredibly simple. I'm just going to state the equation. Okay, what this states is that let me do this twice. I'll do this one for the calculus people and one for the non-calculus people. This one's for the calculus people, and this one is for the non-calculus people. Okay, this is the change of momentum over change in time. And this is a sigma. This just simply means you sum up all real forces, and that's going to equal the change of momentum on a system. So we're going to define a system. Define the system as, the most simple system would be like, say, a particle on the surface of the Earth. There's a particle. Here's the Earth. What force is there? Gravity. So we got, so then we could say the change of momentum over the change of time equals the sum of the forces, but there's only one force, right? Gravity. That's minus mg. Is there any more forces? No. Pretty simple, huh? Now, the momentum, let me define momentum over here, is the mass times the velocity. Now, is the mass changing in this thing? Yes, sir.
Can you go over that water equation how you got that?
This I'm about to. I'm just stating, this is the sum of the forces, so this could be rewritten like this. You guys familiar with the sigma term here? It's just a summation. So if I write that out, it'd be force 1 plus force 2 plus force n, on and on and on, ad nauseum. But there's only one of these guys in this example. You see that? That's the force due to gravity. So we'll call this force sub little g. And the force is the mass of the object times the gravitational pull. Yeah.
Why is it negative?
Give me a second. Let me go back to this. I want to make sure that you guys see this, and then I think it'll make sense to you a little better. This is momentum. It's the mass times the velocity. Now, if I have a delta P, what's more likely changing, the mass or the velocity? The velocity. So then, in most cases, for most cases, the change of P equals the change in V. So I can rewrite this in this case. Mass times change in V over change in T. What is delta V over delta T that we learned from before? Acceleration. Good job, guys. I don't say that sarcastically. Well, what's the acceleration when an object is falling if we define up in the positive direction? It's just negative g, right? Do you see how that's going to work out? The masses will divide out, and the acceleration of this particle will be negative g. Newton's law of work for this, the simple, yeah. Force. Yeah. Now there's something very special about this force, and I'm going to emphasize this. It has to be an external force. An external force. Because if I was wearing boots and I grabbed the hold of my bootstraps and start pulling really hard, am I going to accelerate? No. So this does not imply, that's an internal force. If I define my whole body as the system and I start pulling on myself, like, sorry, if I start pulling on my bootstraps, that's terrible. That wasn't intended at all. I start pulling on my bootstraps, I'm not going to accelerate. Yeah? Oh my God, that's the worst that's ever happened, I think. That may be the experiment I drew on the board that, I drew this experiment on the board that showed how they come up with the speed of light. And it looked like something that it wasn't. And I didn't notice it as I was drawing it. Everybody starts laughing. I'm like, why are you guys laughing? I stood back. I was like, oh my goodness. So that's the result. So is gravity an internal force or an external force?
External.
Depends. Yeah. I'm gonna get to that. When I generalize, I'm gonna go back to this definition. This is I'm helping people that don't have any calculus. So I wanted to talk, make sure that I cover this without using any calculus. And to work these problems, this is all that you're gonna need. And I think in the book, you can actually, I think normally assume that the mass is gonna be constant. So the most common way that you're going to see Newton's law written as the second law is F equals ma. That's so terrible. That's a terrible way to write it. The reason why this is a terrible way to write it is the mass can be changing. What's accelerating? What kind of force is it, external or internal force? And I said the force of gravity. I said the force of gravity is an external force, but it depends on what you define as a system, and this is where it gets really tricky. Beautifully simple equation, would you guys agree? Yeah, and it's a very powerful equation. But this is where you got to really be careful. Uh-oh. I'm going to erase this and then rewrite my equation here, just so that I can have some, This is gonna blow your mind. Okay, say we have two stars, or we could even be fun and have two black holes. Yeah, you guys want to have colliding black holes?
Yeah.
Okay. Now these black holes lie on a center line. They align the center line, so that means as they travel towards each other, they're not going to start orbiting each other. Since they're perfectly aligned, there won't be any angular momentum as they get close. They'll just collide into each other. Okay. Now we're going to call this whole thing the system. Right? And I'm going to put it in a box. Why did I put it in a box? Pay attention, guys. Make sure you... Do I have everybody's eyeballs up here?
It's a system.
I put a box around it to show that, are there any external forces? There's not. So what should the summation of F equal? Correct. So is there any change of momentum? No. And you might ask yourself, well, how is that? If these guys start at rest and they start accelerating towards each other, you got forces, you got change of momentum because you got M delta V over here, you got another M delta V over here. How is there not a change of forces? But you said these are closed systems and it equals 0. How could that possibly be? They do. These velocity vectors are going to be they're going to be equal magnitude if these black holes are the same. Say this is a 10 stellar mass black hole. This is a 10 stellar mass black hole. The masses are going to be equal. Then that means the velocities are going to be equal and they cancel each other out. And that's part of Newton's law here is that whenever a system is closed, that means there's nothing reaching in there, changing anything. The acceleration is the forces, the sum of the forces are going to equal 0. And that means something special. And I told you I was going to go back here. What if I have the first time derivative of something? We don't know what this something is yet. Something.
You forgot to eat.
Something.
Yep.
Yeah.
Something. And I say that it equals 0. What am I saying about the something? If this is a time derivative. There's no change over time. So the way that physicists say that is something, I spelled it right that time, something is conserved. Now I'm all paranoid that I'm going to spell something wrong. Something is conserved over time. Does that make sense? So now somebody asked me, what's the P dot? P dot is dp dt. Right? So if dp dt is the sum of the forces according to Newton's law, and we add up all the forces, and like in this black hole system, it equals 0, what have we said about the momentum? It's conserved. This is the conservation of momentum. We say that as long as there's no external forces reaching into our closed system, momentum is conserved. And we can say this is true if we sum over every particle in the universe. We expect that the sum of all particles and the forces, every force acting on every particle in the whole universe should be equal to 0 if the universe is self-contained. So that's not very interesting in a way, and it's very interesting in another way.
In what way is it not interesting?
In what way is it not interesting is because you can't really work out. If you are always defining the whole universe as your system, you're always going to get the same answer, 0, and you're not going to be able to do any physics. Does that make sense? So in that sense, it's trivial. It's not very interesting. It's interesting from a philosophical point of view, but maybe not from a working problems point of view. Does that make sense? Because if you just say this equals 0, Yeah, you can actually go in and work these out because you can say, well, this has to be equal 0. So,
I've got a question.
yeah.
What if there's, hypothetical here, 2 particles in the entire universe? One remains still, and one is moving away, and they're far enough apart with low enough mass that there's no gravitational effect.
Okay. Is there such thing as being far enough apart that there's no gravitational interaction?
Yes,
No. Because here's the force of gravitation between 2 masses. It's big G, mass 1 times mass 2. We're going to learn about this next chapter, over r squared. So as long as r is not infinite and our universe is not infinitely large, then there's going to be some gravitational effects. No matter how small, it still exists. Okay, and another reason why I said this is not interesting from a physics point of view is because we don't know what the forces are. All we know is that they cancel out. So we can't actually tell how fast this is going to be accelerating towards this guy over here. You see what I'm saying? So what would be better, what would be more interesting is, say this is a particle, just a point, a very tiny mass, like a BB or something, small enough that we can neglect its effect on this body over here. And I would say a BB compared to a 10 stellar mass black hole is, we can neglect the effect of the BB on this massive object here. Is that safe?
Yeah.
Okay. It will affect it. It's true, it will affect it. The momentum is still conserved, but we're going to ignore that. And then we can close this off, and now we can say the change of momentum, or sorry, we can bring the mass out now because we're going to say the mass is constant. The change of velocity over the change of time equals this force over here. This is the gravitational force. And we're going to learn that later, so don't worry about the details. And r is the distance between them. So now we can do some physics. We can actually find out what the acceleration is, because this equals acceleration. And one of these masses, say mass 1 is the mass of the BB. What's going to happen to that mass? You can divide it out, right? So then the acceleration due to the gravity of the black hole is just the mass of the black hole times this universal gravitation constant, which is true for the whole universe, divided by the distance between them squared. And now that's more interesting than someone over making everything, the whole thing a system. Now you can call whatever you want a system, you just have to be consistent. You can't at one point make it part of the system and at one point not make it a part of the system. You gotta just make up your mind in the beginning. What's a part of the system and what's not.
So is it just that one that canceled out then?
Correct. Yeah, then the acceleration, and that makes sense because the acceleration here on Earth is due to the mass of the Earth, not really due to the mass of the object, right? Because I could drop a heavy object and I could drop a light object, and they're both going to fall at the same acceleration. And the beauty is you see that here. You see that no matter what the mass of that lighter object is, it's going to divide out and it's going to be the same acceleration. That's exactly what we expect. So this works. Yeah? All right. So I'm going to erase this now. Have I made a good compelling argument here? Okay, let's just start. I told you that was going to blow your mind. So then I'm going to go back and leave this, just as I stated before, for calculus people, P dot equals the sum of the forces. And I'm going to call these, I want to put a little notation to remind you, these are external forces. Yeah? That's what the E stands for. So for you guys that already wrote this, you might want to do that little, make that little add there. It's external forces. For non-calculus people, it's change of the momentum over change in time is the sum over all I. These are forces are external to the system and how we define it.
Is that also part of his first law or is part of the second law?
They're related, but no, they're. I'm sorry. Is that why?
Yeah.
Okay, my bad. Thanks for catching my error. So now you should understand what this means. When I say this, these are external. This is a change of momentum. And can you see that this idea is a lot more powerful than just saying F equals ma? Because we're very careful. This is a very careful way to state it. And you'll see it'll work quite nicely. I'm going to do some more examples, and I'm going to end with a very difficult example.
Could you
Yes.
possibly like put it into words instead of just translation as well?
That's what I would advise you to do. I would strongly advise everybody to go back and watch this video. And what I would do is on your notes, just write all this stuff that I'm saying verbally. Just write a lot of it out, because I'm going to post this on YouTube. As long as he doesn't forget to restart the video after half an hour. Does it look pretty good? The resolution on this camera is very good, so you'll be able to see everything fine.
You said it's 4K. Is that the 4K?
I'm not recording 4K right now. I'm recording a high definition, but there's plenty of detail there. I've done this for my professors, and it's a huge, well, yeah, it's a much longer chalkboard, and I'm like zooming in as they're panning across, pan across the board as they fill up the whole board, and I go back and watch it. I can read everything, no problem. Okay, number 3, for every action force, there is an opposite reaction force. Okay, so let me explain what I mean by this. Some people, when they do the sum of the forces, they make a mistake, and they list MA as a force in here. It's not a force. It's a reaction to the sum of the forces. It's a reaction of the particle to the sum of the forces. It's not a force. There's nothing, this is the cause of the other forces. Do you see that? So putting this on this side of the summation sign, sorry, I didn't mean to do that. Putting this over here with this in the summation, and then you're adding other forces or whatever, and then you got, this is where the MA goes. This is an error. Because this is the result, I'll say it again, this is the result of forces on this mass. It's not a force itself. You might call this inertia. So you could say the sum of the forces equals inertia. So if you try to push something, it fights you, it pushes back. But if you were to actually work a problem, say with a boy pushing a cart, or a girl, it doesn't matter, I'm not sexist. You probably can't see, can you see that over there?
Yeah.
Oh, you can't, okay.
Well,
So if you got a boy pushing the cart, to make it interesting, right, you got to be careful how you define the system to make it interesting. You have to say that the boy's external force, and this is where your drawings are super important when working on these problems, because you're going to draw out the forces. You're going to draw the force of the boy, maybe draw it external to the box. So the force of the boy, and then the boy is going to feel a force pushing back, and you'd call that inertia. But that's not, according to how we define the system, that kind of stays in the system. Does that make sense?
it reached 29.
29?
29.
All right, I'll stop it here and restart it.